Screen. All right, can everybody see that?
Yep.
Yeah.
Good. So this is where we were last time. We said we want to consider, well, we said that we could take the path, the amplitude, and split it up into the sum of two amplitudes. One, the sum over direct paths, and by direct paths, I mean this, and one, the sum over exchange paths, the one on the right-hand side, okay? And then we changed coordinates and we went to relative separation coordinates, in which case in relative separation space, I had those two paths being these two. And these two paths are not identical. In fact, they lie in different equivalence classes because the configuration space is a doubly connected space. And by doubly connected, we mean in particular R3 less the origin. So in principle, I should subtract off the origin. R3 less the origin. Let's put a circle around there. Modded out by Z2. Okay. Which told us that our amplitude can be split up into two separate parts, one of the sum over direct paths and the other one the sum over all paths in which the particles are exchanged. And then we can, we left off where we said, okay, now let's consider some one parameter family of amplitudes, which are defined like this, where that one parameter was the phase that separated out the direct paths from the exchange paths. Okay, so today I want to finish up this computation and show you how bosons and fermions arise in D equals 3. And then we'll go down one dimension to D equals 2. So D, little d is the number of spatial dimensions. So we'll go down to D equals 2 and look at particle statistics there. In particular, we'll examine the concept of fermions and bosons in D equals 2. And we'll show that it's slightly less meaningful in two dimensions, in two spatial dimensions. In particular, this will give rise to the idea of anyons, which are particles which have any statistics really, not just bosonic or fermionic statistics. And then if I have time today, otherwise I'll do it on Monday, I will talk about the uses of anyons, the current uses of anyons in the idea of quantum computing. And in particular, this is going to be relevant for a particular slant on this idea of quantum computing. This is what's called topological quantum computing, where some set of people, largely sponsored by Microsoft, are looking to use anyons as qubits, as quantum bits. Okay, so let's get started then. All right, just pull up the video. There we go. So I can have a look at you guys as well. Okay, so to start off with, let's consider an open path as distinguished from the closed paths that we were considering previously. So in this case, I want to look at paths in R space that are not closed, and so we're evolving from R to some point R prime. So recall then that what we were doing was considering this one parameter family of amplitudes given by R prime T starting at R naught, and these are vectors in R3, and this is given by A bar R prime R naught plus e to the I phi A bar minus R prime T R naught. Okay, very good. So now let's look at the following. Remember that R and R prime are not the same now. But what we can do is we can move R prime continuously from R prime to minus R prime. So now let's send, so now let's continuously move R prime to minus R prime. In which case, my amplitude A phi goes to minus R prime T R 0. And everywhere I see an R prime, I change it to minus R prime. So that looks like that. Okay. So what does this plot mean? Well, I also know that the two particles are identical, which means that the R prime configuration and the minus R prime configurations are really the same thing, which means that the two amplitudes describe the same physical process. So these two guys here describe the same physical process. And if that's the case, then that necessarily means that they can only differ by, at most, a phase. So this means that a phi at R prime T R naught and a phi at minus R prime T R naught can at most differ by some phase like e to the I alpha. All right. If we cast this in the language of the amplitudes that we were doing in the covering space, then this means that the following is true. It means that a bar of R prime T R naught plus e to the I phi a bar of minus R prime T R naught must equal to e to the I alpha, sorry, let's give ourselves more space. E to the I alpha, that's that phase factor, times a bar of minus R prime T R naught plus e to the I phi a bar of R prime T R naught. Well, now I can equate coefficients of the amplitudes and see what I find. So equating coefficients I'll find two things. One is that alpha and phi must be the same up to factor of 2 pi, modulo 2 pi. And two, that e to the 2 phi I must be 1. Well, the second of these two equations has two physically equivalent solutions. Either phi equals 0 or phi equals pi. So this necessarily means that either phi equals 0 or pi. Okay, so this is important. Why? Now we can assign some interpretation to this story. So if phi equals 0, let's take the phi equals 0 case first. Phi equals 0, then the following is true. Then the amplitude for exchange is a bar, or the total amplitude, sorry, is given by the sum of amplitudes between direct and exchange. And it's this minus sign here that makes all the difference in the world. When I have such a minus sign, I'm talking about bosons. This is what I would expect for bosons. You exchange the two particles, nothing changes. On the other hand, if we had phi equal to pi, then we would find that the amplitude comes with a relative minus sign. Minus, because e to the I pi is minus 1. And this minus sign tells us that we're talking about fermions. So in 3 dimensions, the path integral gives us a really neat way of understanding how quantum particle statistics arises. Okay, it's a question of the two different types of paths that I can have, direct paths or exchange paths. And if you look at this, you would think that this would be a dimensionally independent analysis, in the sense that, we didn't really need to make use of the fact that we were in 3D in anywhere in this argument, right? So you would look at this and you'd say, well, we didn't use the fact that we were in 3D, in 3 spatial dimensions anywhere. So why should this depend on, how many dimensions we're in? And it turns out that that intuition would be exactly wrong. So to show you why, let's go down by a dimension. So now I want to go down to two spatial dimensions. So now let's consider two identical particles in D equal to 2. Okay. Where now R, the position vector, has components in the x direction and y direction only. Okay. Again, we're going to go to relative position space. Again, the center of mass position is going to be irrelevant to this story. And again, we'll find that the total amplitude, the total amplitude A of R prime T R 0 is a sum over pods, and it will be a sum over direct pods and exchange pods. And here's the difference. Now we have to try and understand what we mean by exchange pods in 2 dimensions. So it's going to be a sum over pods of the form e to the I s, and s is a functional of R of t. Okay. So the sum is taken over. The sum is taken over all pods that join R to R prime. So in 3D, we had 2 types of pods, either direct path or an exchange path. Okay. In 2 spatial dimensions, in fact, there are an infinite number of different classes. To see why, let's draw a picture. And I want to draw the picture in relative coordinate space. And I'm just going to draw 3 typical pods, characteristic pods, if you want. All right, so they're going to be first one, second one, and a third one. And again, I'm going to remove the origin because I'm going to consider 2. I'm going to consider 2 particles that interact with some infinitely strong. Sorry, just give me 1 second. Actually. Okay, so let's take away the origin, and this is our relative coordinate space. And again, we're going to draw different classes of pods. So for the first one, R, that's the first class of path. Second one is going to start at R. And end at minus R. And the path itself could look like this. And then the final one it's going to be different in this case, and you're going to see where the infinite class of paths comes from, is one that starts and ends at R. However, it encircles the origin. So these three different paths correspond to, actually, sorry, my bad. We're in 2 dimensions. So our relative coordinate space is 2-dimensional. And it looks like this. So this would be or X or Y. Okay. So these three different paths in relative coordinate space correspond to three different trajectories of the particle. And because of the indistinguishability of the particle, again, we have Z2 identification, and all these three paths are in fact closed paths, right? Physically, they correspond to the following pictures. Physically, these closed paths correspond to the following. So in this story, time is going to go upwards. Pick a color. There we go. Time is going to go upwards like such. And my particles are going to look like this. So we're going to start off here. This is the first picture. And the particles have the following world lines. And this is the direct path. The next set, the middle picture in the previous slide. So this one corresponds to an exchange path. So here, two particles are exchanged. Again, they're indistinguishable particles. But that would look like that. And then finally, I have the following trajectory that is new in this story. This one looks like this. In 2 dimensions, these are all different trajectories. So the first two are the 2-dimensional analogs of what we found in 3 dimensions already. But the third one is not a permutation of the particles and topologically distinct from the other two. So this is a topologically new Okay. And we can characterize, if we want to do an analysis of this now, we can characterize each path. We can characterize each path by the polar angle formed between the start and the end vectors through a full traversal of the closed path. Right? Clearly, looking at this picture, this number is going to be some integer multiple of pi, with positive integers telling me the positive winding and negative integers telling me the same winding but going in the clockwise sense. So in this sense, this path here corresponds to n, that integer, equal to 0. This path corresponds to n equals 1, and this path corresponds to n equals 2, keeping in mind that r and minus r are identified in the story. Okay. So what this means is that instead of summing over, some hand-wavy definition of paths, I can now tell you how to sum this amplitude. So in terms of the amplitude, this means that I can write A of R T R naught equal to a sum over what is effectively the winding number of paths computed in the covering space and labeled by n R T R naught. Right? And again, we can generalize this relation by adding in some phases. Let's call the phases Cn in this case. So we're just playing the same game we played in 3 dimensions. We get that A of R T R naught is the sum over n in a set of integers of this Cn A n R R T R naught. Okay, so now we need to see what the possible restrictions on these Cn are. Okay, and we do what we did the last time, and we assume that the start and end points are no longer the same, so that if we label our amplitude by a polar representation, so I'm going to define this thing to be A of R prime theta prime. Right? This R is a polar angle now. So r and theta are polar coordinates. So in that case, I'm going to be able to write my amplitude as a of r prime theta prime equal to the sum over n and z of Cn a bar n of r prime theta prime. So now we'll continuously change theta to theta plus pi. So remember, in the three-dimensional case, we sent r prime continuously to minus r prime, and we identified those two. Well, we're going to do the same thing here. So now send theta prime to theta prime plus pi. In that case, my amplitude reads r prime theta prime plus pi, and this is equal to sum over n z of Cn a n bar of r prime theta prime plus pi. Okay, which again, as it did in 3 dimensions, corresponds to the same physical configuration, which means that this guy has got to be something like e to the in this case, I'm going to choose just by convenience, I'm going to choose the phase difference to be minus I phi a of r prime theta prime. So if I shift theta by factor of pi, then the amplitude can at most change by some phase. I'm going to write that phase as e to the minus I phi in this case, right? Moreover, and this is an important point, my amplitude a n bar of r prime theta prime plus pi is actually a n plus 1 bar of r prime theta prime. And I'm going to leave as an exercise for you to understand why this is the case. As a hint, I'll tell you that you should think about a multi-sheeted Riemann surface. Okay, so let's put these ideas together. And when we do, we will find the following is true, that e to the minus I phi times the sum over n of Cn a n bar of r prime theta prime is equal to sum over n of Cn a n plus 1 of r prime theta prime which is equal to, just relabeling my summation index, the sum over n of Cn minus 1 a n bar of r prime theta prime. From which it follows then that Cn is just e to the I phi Cn minus 1, which is why I chose the minus sign here. It's hell of a convenient for this fact. And this is a recursion relation for the phases Cn. With the initial condition for the recursion relation, which is a discrete type of differential equation, if you want, that C naught is just 1. And if I take C naught to be 1, then I can solve this recursion relation. In fact, what it means is that the nth phase, Cn, is just e to the I n phi. So that's cool. I know exactly what these phases must be. But if I know what these phases must be, I can just write down the full amplitude then. The full amplitude, A, is just the sum over n in Z of e to the I n phi times a n bar. Right? And here's the crucial thing. We've worked out all the constraints that come from the amplitudes, and there is no restriction on phi. We could choose phi to be 0. We could choose phi to be pi. These will give us bosons and fermions, respectively, but we don't have to. And this is the key thing, right? So there is no restriction. So no further restriction on phi. So phi equals 0 will correspond to bosons. Phi equals pi will correspond to fermions. As usual. But phi equals anything else is allowed. This corresponds to what are called anyons, which are special particles that exist in 2+1 dimensions that do not obey bosonic or fermionic statistics, but a whole different type of statistics by themselves. And this is the basis for what's called topological quantum computing. So the idea in quantum computing is the following. I want to generalize away from classical bits that can be either 1 or 0 and that I can make using electric circuits. Turn them on, turn them off. That gives you 1 or 0. This is the classical binary bit. In quantum physics, we know that you can have a superposition of 1 and 0. This results in something called a Bloch sphere. And it tells you that you can generalize the idea of a classical bit to a quantum bit. And the quantum bit is a superposition of 1s and 0s that is, in principle, allows you to do significantly more computation with more memory and harder problems than a classical computer. And keep in mind that all the computers you've ever met so far in your life have all been classical computers. The question then becomes, what do you use for a qubit, for a quantum bit, if you can't use an electric circuit that's either 1 or 0 anymore? So there are many different ways of thinking about what a qubit is. One that I like most, and I don't usually like Microsoft things, but one that I like most, in fact, is this idea that comes from anionic physics on a plane. And the idea is the following. Because these paths that we were talking about are topologically distinct paths. Essentially, I get what's called braiding statistics that tells me that in order to deform this path here into either this one, or for that matter, an infinity of other ones, I have to do something drastic. I have to cut this path, right? If I don't, then this path is topologically distinct from this path, which is topologically distinct from that path. So what does that mean? Well, that means that I could come up with a qubit built out of the braiding statistics of these anyons that are stable, topologically stable, which means that I have the possibility of building a computer using these qubits that is stable to thermal fluctuations, because they don't really care about thermal fluctuations, and it's stable to scaling. I can build more and more of these things by adding more and more qubits in different topological classes, and I can build a stable, large, I mean, not microscopic, quantum computer. This is the idea of topological quantum computing, which is what Microsoft is working on, in particular at Microsoft Station Q in Santa Barbara, and it's headed up by Fields medalist Michael Friedman. Unfortunately, we have yet to produce a stable anyon in a lab situation that's reproducible. And so consequently, while this is the prettiest version of quantum computing, in my opinion, it is also the one that has the least success at the moment. Okay, thanks very much. Any questions?